Mathematicians.
Okay, let's get started. Let's get started, please. So remember what we are doing. We are in the middle of the Stone-Weierstrass theorem. Stone-Weierstrass, right? Which said that given any function that's continuous on some closed and bounded interval, there exists a sequence P sub n of polynomials such that P sub n converge to F uniformly on AB. Okay, that should be in your notes. Right, and we made some assumptions about the. Right, we reduced the problem a little bit. We made some assumptions that AB was actually 0, 1, that f of 0 and f of 1 were both 0, and that f of x was 0 outside of 0, 1. Okay, so we have uniform continuity, right? So that f was uniformly continuous on all of R. Okay. Okay, and our idea was to create an approximation of the identity, and then use that approximation of the identity to construct the p's, right? To construct the polynomials. So the proof was that we would let q sub n be defined, and these are what are called the kernels. The kernels. The q sub n are 1 minus q sub n of x is 1 minus x squared quantity to the n on negative 1, 1, where c sub n was defined so that the integral was 0. Right? C sub n is defined as the integral of as 1 over that integral. Okay. And we observed that. So this is all, but just for completeness, let me reiterate it. The integral of each of the q sub n's was 1, of course, right? And you'll see why that's key in a second. And 2, for any lambda between 0 and 1, q sub n converges to 0 uniformly outside of the neighborhood, the delta neighborhood of 0. So on the interval, on the set where the absolute value is between lambda and 1 inclusive. So these qualities are maybe what makes it good. Okay, so last time I said that in some other book that we'll actually be switching to during this class, they call this thing, instead of the method of approximation of identity, they call it like the method of using good kernels. These are the kernels, and this is the goodness of them. Okay, that they have the integral is 1, and they have this decreasing quality. Okay, and so you've seen all this before. We just justified it last time, and now we construct the p sub n's. Right? The p sub n's are constructed by taking what's called the convolution of f and q sub n. Okay. Okay. So notice that if we change, we can do a change of variables on this and it'll change to this integral between negative x and 1 minus x of f of x plus t qn t dt. Okay, and then we can do another change of variables that changes it to the integral between 0 and 1 of f of t qn t minus x dt. Okay. So this is just done by change of variables. Yeah. All right.
So we have an x plus t in the second line?
Yeah, that's an x plus t. Hold on 1 second. I'm sorry, this is not a change. Sorry. This should have been a plus to begin with. Sorry. Thanks for asking me what's going on here. Okay. So yeah, so this first step is not change of variables. The second step is a change of variables. Sorry. This is by.
So can you change the limits?
So what's happening here? Why do we truncate the interval, right? We're looking at f of x plus t, right? We only have to let t go up to 1 minus x, right? Because f becomes 0 after 1, right? Remember what f was? F was this function between 0 and 1. It has something, but then after that it's 0, and before that it's 0, right? Okay. So, taking that into account, we only have to think about this interval, right? So this is using the support. So since f lives on 0, 1, right? We can change it to this, right? T only has to go from negative x to 1 minus x. Okay.
And where is that region on the figure that you've drawn?
So x is right. X is some number between negative 1 and 1. Okay. So whatever 1 minus that number and minus that number. Okay. And then we do a change of variables. So this one's change of variables, then we get that. Sorry. Okay. But think of what this is, right? This is the integral from 0 to 1, f of t, c sub n, t minus 1 minus x squared, right, quantity to the end of t. Right? So when you integrate this thing out, what are you going to get? Right? Well, the t's are going to be integrated out, and what you have are powers of x, right, multiplied by some numbers, right? In other words, this is a polynomial. Right, this is a polynomial in x. Right. Is that clear? Is that clear? Right. Think of it this way. Suppose this whole thing were just the letter x. Okay. It's not, but it's basically that's what's going to happen. Okay. Suppose this thing were the letter x. Well, I just pull the letter x out, and I have some number times x. Right. It's not the letter x, but it's it's powers of x. It's going to be powers and it's going to be some linear combinations of powers of x, right? Right? You're going to get some numbers times those powers of x. So it just turns out to be a polynomial. Okay. Okay, so now we've got our polynomials, right? We've constructed our polynomials. Is everyone okay? I feel like you're not okay. Yeah, Thea.
I'm a little confused by the change of variable. So you're replacing t with t max. Wouldn't you get as, it might not be very basic right now, but wouldn't you get minus 2x going to 1 minus? Wait, no. Yeah, minus 2x going to 1 minus 2x.
For the balance of this thing, let me think for a second.
X is 0.
T minus x, right? So
You're replacing t plus x.
yeah, so t minus.
T minus X.
So let t be like. Let me change the variable completely. So let s be x plus t. Okay, let s be x plus t, right? And this is going to be f of x, right? This is going to be s minus x, right? S minus x, right? Right, because t is s minus x, right? And we have a ds here, right? And when t is minus x, x is 0. When t is 1 minus x, we get a 1. No, this is better. You were not lucid. as you guessed. It's okay. 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 That's fine. I spend 99% of my life being not lucid. So. Okay. Okay. So now we want to prove that we've got our polynomials, and we want to show that they converge uniformly. Okay. So let's prove that the piece of n converge to f uniformly. Okay. In other words, so let's fix an epsilon, right? We want to show that there exists an n such that n bigger than n implies that Pnx minus f of x is smaller than epsilon for every epsilon in our domain. Okay. Okay, and we'll use basically what is the standard argument when you're doing an approximation using the method of approximation of the identity. Say, okay, well, let's think about this. Well, this Pnx minus f of x is, by definition, I'm just going to substitute for piece of n, right? It's -1 to 1, f of x plus t, qn t dt. Okay, minus f of x. Okay, I haven't done anything yet, right? And then we're going to use the usual trick, which is to remember that the integral of this thing is 1, right? The integral of this thing is 1, and so we put in a 1, okay? And the 1 looks like this, right? We put in a 1. Here it is. Okay. It's always okay to multiply by 1. Right? It's always okay to throw in zeros. It's always okay to multiply by 1. And this is what we do all the time. Okay. So this is a standard trick. So in other words, what I could have done is basically say I can slide that constant inside here. Right? I can slide that constant inside here. -1, 1, f of x plus t minus f of x Q and T dt. Right? Right? Normally we don't write out this part. We just say, look, you know, the integral of that is 1, so I can slide that constant into here. Okay. Okay. Why do I like to do that? I like to do that because it allows me to take advantage of continuity, right? My function is continuous, right? And so I know I can control the size of this thing, right? I can control the size of this thing to some, at least within a certain neighborhood, right? So so you say, okay, well, let me use first the triangle inequality to go like this: f of x plus t minus f of x, right? Q and t dt. So, right, the absolute value of the integral is less than or equal to the integral of the absolute value, right? The absolute value of an integral is less than the integral of the absolute value. The continuous triangle inequality, right? This is also the triangle inequality.
Would it matter if we include Q and T as well?
I should. So really I should have this, but remember what Q is. Q is something squared.
Integral.
Remember what Q and T was, right? It was, you know, Cn 1 minus T squared to the n, right? Right, where T was between, T is between -1 and 1, and so that's going to be positive. Okay, so I don't need that. Okay, so now I say, well, now I'm going to use continuity, right? What's my goal? My goal is to make this thing small, right? My goal is to make this thing small. So now I have control over this thing, so I say, okay, well, so I'm gonna break this into two. No. Let's say it this way. Okay. No, I'm going to write it this way. Okay. Sorry. So I'm going to break this into two parts. Okay. So I'm going to break this into the part where t is an absolute value small. Okay. And I haven't chosen what delta is, but I'm going to break it into two parts, and I'll choose the delta in a second. Right? I'm going to choose it where t is small and the absolute value of t is large. Right. So I get this thing. And I get this thing. And this more space. Okay.
Can you hear what the upper bounds of the integral?
These are the upper bounds are included, right? So t lies between negative delta and delta. And here I've got the integral, so t goes between -1 and negative delta, and also between delta and 1. Okay, so anyway, just let me write it more concisely. Okay, right? And maybe you see what's going to happen. What's going to happen? On this part, right?
If t is less than delta, then it's continuous, and we know f of x plus t minus f of x is less than epsilon.
Yeah, so we can, right, if our t is small, then we can use continuity to control this thing, right? Okay. When our t is large, we don't have that control though. However, we're on the space where we're in the domain where. What was good about this domain? Q goes to 0. Q converges uniformly to 0, right? So we've got our two things that we can play, right? We break it into two parts. In the first part, we play the continuity. In the second part, we play the convergence to zero, uniform convergence to zero. Okay. Okay. So this is like the standard sort of splitting trick. Right. We use the continuity on one part, and we use the the decay on the other part. The convergence to zero on the other. Okay. So how do we choose? Delta? Well, f is uniformly continuous. So we know that there exists a delta such that if the absolute value of t is less than delta, then f of x plus t minus f of x is smaller than epsilon over 2. So that's the delta we're going to use. Okay, so we get that this thing is less than or equal to epsilon over 2 times the integral of qnt dt. Right, for this first term, right, we can pull out this thing is less than epsilon over 2. We pull out that epsilon over 2, we get the integral of this guy on that tiny neighborhood of 0.
Is that equal sign should not be like less than equal then? Because we're still relative, like that relative to like the original like
What equal sign?
nx.
Just
like,
splitting
like
trick?
right above, like below splitting trick.
That refers to the equality of the two things, though, right?
Is
No,
that
this is
referring to
equal.
the one above that, or?
This is equal.
Yeah,
This is
that.
equal, right? Because we're just splitting the negative 1, 1 into two parts, right? We've got negative 1, 1, right? Here's 0. And we say, we're going to break this into two parts. The part within delta of 0 and the part not within delta of 0.
But relative to the original equation, then it's less than.
Yeah. But that's not how you write. That's not how you use your notation, right? If I write equal here, it doesn't mean equal to this, right? It means equal to this, right?
I'm like looking at it like vertically, so I'm just like.
Oh, I see what you're doing. Do not. Okay, maybe I should put an extra equal here, an extra equal here. Is that better?
Yeah.
So it's actually one long line. It's not a vertical thing. Yeah, I see.
Sorry.
No. That's sort of reasonable. Okay. Yeah, I had a professor who always would put an equal at the end and then keep on going, and I always wondered why he did that. But now I see why. Okay. Okay. Enough going around. Okay. So we have this part. We can pull out the epsilon over 2, and we have this thing, right? The other part, which we haven't fixed yet. We haven't dealt with yet. Oops. Okay. Now, now here we're sort of in trouble, but we're not really in trouble because we know that this thing converges to zeros uniformly. Okay. So on this part, we have only crude control of f, right? We can't really control this difference, right? F of x plus t minus f of x, right? We have that f of x plus t minus f of x is smaller than some 2m, say, right? Where m is the bound, m is the bound on 0, 1, on negative 1, 1. right? You've got a continuous function on a closed and bounded interval, so it's bounded. Right? Okay, so we've got at least this crude bound, and that's good enough, right? Right. So, right, we get, this thing is less than or equal to epsilon over 2 times the integral over negative 1, 1 plus 2m times the integral over this region away from the origin. Right, and you see what we're going to do. Okay, so take 20 seconds and write down the end.
A quick question.
Yes.
How do we know that we have any sort of bound on this? Did we already?
Well, your function. Remember, your function is continuous, right? Your function is continuous, and you're on this closed and bounded interval, right? So by the extreme value theorem, you know that there's going to be an upper bound and a lower bound. Yeah, Pam.
Is the function uniform?
It is, right? Because it's continuous on a compact set. Okay, turn to your neighbor and just talk for a minute, and then I'll write up the answer. Okay, so somebody has a question, which is, how do we get from, we were doing this integral and then I switched it to negative 1 to 1. Why is that okay?
It's only defined the support. The support is linear.
That is the support of Q, yeah, but why was it okay for me to switch from integrating over this tiny interval into the integral over the whole interval?
Has delta, isn't it just equal to 0?
It's not, no, that's not what we're using. But remember, this thing is positive, right? Right? And so when I switch the integral over the whole interval, it just gets bigger.
So it's less than
Right?
equal to-
It's okay for me to do that because I'm just making things worse for myself. Okay. And the reason I did that is because the integral of this thing over negative 1 is 1, right? So I can get rid of this. Right? This is 1. Right? At the very worst, I get 1 here. Okay, so you know what I want. I want to make this thing, smaller than epsilon over 4m, right? So that this whole thing is smaller than epsilon over 2, right? So, and that's okay, right? So why is it true that since Qn goes to 0 uniformly on that domain, uniformly on that domain, we know that, right, that the limit of the integrals as n goes to infinity, the limit of the integral of this thing equals the integral of the limit, which is 0. Right? We can interchange by uniform continuity. right? This is one of the great things about uniform continuity. We can interchange integration and limit, right? So what does that tell us? So there exists an n such that if n is past it, then this integral is smaller than epsilon over 4n. Right. Right.
Professor?
Just a second, right? And thus, we get, less than or equal to epsilon over 2 plus 2m times epsilon over 4m, which is epsilon. Yeah, Lara.
So we know that that Qn as a function goes to 0, right? But then I'm a little confused about how can we say the same thing about the integral? Because we know that the function's convergent.
That's exactly this thing here, right here, right? So you say, well, look, Qn goes to 0 uniformly, and we had that theorem that said that if that happens, then the limit of the integrals is the integral of the limit, right? Well, the limit is 0, right? So the limit of these integrals is 0. Okay, so what does that tell us? That tells us that these integrals go to 0. Okay, yeah. These integrals go to 0. And so we use that. Yeah, Theo.
Could you also use just uniform convergence?
Yes, just use it directly. That's fine. Yeah, it's just kind of nice. Yes, you could do it directly. That's fine. Okay, so that is the end of the proof of Stone-Weierstrass theorem, the Stone-Weierstrass theorem. What we're going to do from here on is we're going to skip to a little bit of Fourier series, and that will involve some of these notions. Okay, we'll need to introduce one more notion called measure zero, but after that, you'll have all the concepts that you need to get the Fourier stuff that I'll introduce next week.